Look at a vintage alarm clock radio. To keep accurate time and process a signal, its internal components require a steady drip of electricity. Compare that to a toaster. To toast bread, the device has to gulp down a massive amount of electrical current, converting energy into extreme heat. Despite their different roles, both devices share a critical vulnerability. If you push too much energy through their circuits, the materials simply cannot handle it. Take a common LED, hook it directly to a 9-volt battery without regulation, and the overwhelming surge makes the component violently burst into sparks. Electricity itself is an invisible, highly volatile force. To use it safely, we need a mathematical way to predict and control how it behaves before we ever flip a switch. In 1827, German physicist George Ohm published a discovery that changed engineering. He proved that in most materials, there is a perfectly linear relationship between three variables: voltage, current, and resistance. This equation, V equals I times R, became the standard for calculating how to safely harness and scale electrical energy for the modern world. To understand why that mathematical formula works, we first have to shrink down and look inside the wire. A conductor is a rigid grid of atoms, with electrons bouncing chaotically between them. Voltage is the pressure forcing electrons in one direction. Current is the flow rate passing a point. Crashing into atoms creates resistance, slowing the flow and generating heat. This microscopic reality of pushing, flowing, and crashing is exactly what Ohm's algebra represents on paper. By moving from the chaos of atoms into the clean realm of mathematics, electricity becomes a predictable engineering tool. Engineers use the Ohm's law triangle to solve for what they don't know. By isolating the variable you need, you can find the exact resistance or current required for any circuit. A simple way to remember the core relationship is the VRIII rule. Just think of the sound of a speeding car slamming its brakes. Voltage equals resistance times current. Let's apply this. A 9-volt battery provides too much pressure for a 2-volt, 10 milliamp LED. To prevent an explosion, a resistor must absorb the extra 7 volts. By dividing 7 volts by 0.01 amps, the math perfectly dictates a 700-ohm resistor. By doing the algebra first, we can perfectly bottleneck the microscopic flow and neutralize the battery's destructive power. However, there is a catch. Despite being called a law, Ohm's discovery is actually a highly accurate approximation that mainly applies to standard metals. On a graph, an ohmic material shows a straight line, double the voltage, and current doubles. But non-ohmic devices, like filament lamps, don't follow that rule. In these materials, resistance isn't fixed. It changes dynamically as temperature rises or voltage shifts. Even with these complexities, pioneers like Thomas Edison relied on these foundational principles of resistance to build the first electrical grids and massive battery-powered vehicles. Today, even working with advanced semiconductors, V equals IR remains the essential starting point for every electrical engineer. Ohm's law provided the calculation required to turn a chaotic, invisible danger into the predictable energy that built the modern world.